we're now ready to prove the Fubini tonality theorem. And in this video, I'm going to prove a easier version of the Fubini theorem. And then this will lead us to the full theorem in the next video. Okay, so first of all, let's prove the following proposition. Suppose I have two sigma finite measure space. So here sigma finite is really important. And if I take any E inside the product sigma algebra, then the following thing happens. So first of all, the map that maps X to the measure of EX, and also the Y maps to the measure of X maps to the measure of EX, and Y maps to the measure of EY. They are both measurable functions, okay? And the second, because they're measurable, now I can integrate with respect to X and Y respectively, and this integral is going to give me the product measure of the set E, okay? So I call this little Fubini theorem for the characteristic function, basically. Okay, so the idea is once we prove these Fubini theorem for characteristic function, we can move on to, first of all, linear span, so we get for simple function, and then we approximate all the measurable function, and that's the full Fubinian tonality theorem. Okay, so I'm going to prove this little proposition in this video, and we're going to prove the full theorem in the next. All right, so to prove this proposition, so let's first prove the case when actually the two measures are finite. Okay, we're going to worry about the sigma finite later on. So when they're finite, okay, so I want to show that all the E inside the product sigma algebra satisfy these a bunch of these properties. So let's call these properties star, okay. So there's one little trick is that let's call I set C to be all the subset of X cross Y such that the star works, okay, the star just works, okay. So essentially I want to show that the product sigma algebra is a subset of the C, so everything inside the product sigma algebra satisfy star. Okay, so how I'm going to do that is, first of all, let's call a collection F to be all the finite disjoint union of the boxes. So finite disjoint union of sets of the form AI cross BI, they're the boxes. We know the sigma of F from several videos earlier. We saw that this is essentially the product sigma algebra. So this is a cross B. So what I want to show is the following. So first, I want to show that F is actually contained in C, okay? And second, I want to show that C is a monotone class. Okay, monotone class we defined in the end of the last video is a really technical definition. But if I can prove these two, then you see, because it's a monotone class containing F, then what we know is that C is containing the smallest monotone class we used in notation M of F. And there's a theorem from last lecture, we skip a lot of detail, but the idea is the monotone class, the smallest monotone class containing algebra is just the sigma algebra it generates. Okay, so, and I know the sigma algebra it generates is the product sigma algebra. So that will finish the proof. Okay, so the C will contain these A cross B. All right, so let's prove these two things basically. So first of all, I want to show that F is inside these collection of C. Okay, so first of all, it's quite clear if your E is of the form A cross B, okay, that's going to be inside C, okay? Well, why is that? Well, because these EX we saw from last time, well, it just depends on whether your X is inside B or not. Okay, so if X is inside A or not. If X is inside A, then E of X is just equals to B. And if X is not in A, okay, that's just going to be the empty set, okay? So as you can see, the nu of these EX, okay, they're just going to be either the nu of B when X is inside A or 0 when X is not inside A. So basically you multiply by the characteristic function of X, okay? Well, this is regarding X, this is a constant. So the map from x to this constant times the characteristic function, this is measurable. And similarly, you can show that the y maps to mu of ey, that's also measurable, so that's simple. And another thing is you can show that the product measure of this set E, which by definition we saw that on these boxes is just the product of their measure. Okay, this is the integral of the nu ex d mu x. And similarly, you can show this is the other way. Okay, the mu of ey d nu of y. Okay, this is really just because the nu of ex is equals to the characteristic function scaled by the measure of b. Okay, so this is really easy. Okay, so all of these boxes, we can clearly see this inside this collection C. Okay, so if E is equals to A cross B, that's going to be inside C. All right, so now I want to show that C is closed under our disjoint union. Okay, so suppose I have E1 up to En finite disjoint. So they're all disjoint, and each of these EI is inside C. Okay, so because they're disjoint, if I look at their, let's let E to be their disjoint union of these EI, okay, I going from 1 to n is a finite one. So EX is just the union of this EI of X, and is actually the disjoint union of the EI X, okay, the X section of each of these EI, and they're disjoint as well. All right, so the map where you map X to the nu of EX, the nu of EX is just the finite summation of nu of these EIX. And each of these nu of EIX, that's a measurable function. Okay, so your map from X to nu of EX is a sum of a bunch of measurable functions, so this one is measurable. And you do the same thing for Y. I'm not going to write it. And if you want to compute the mu cross nu of this E, okay. So because this is a product measure and you have a disjoint union, so this is nu cross nu of these EI, and you do the summation. And each of these EI, you can write it as the integral of, for example, the nu of EI of X, and you integrate the X, the mu X, okay? And everything here is finite, so you can interchange the summation and the integral, so you move it, the summation inside, so nu of EI X. And this one is essentially just nu of E, okay? So this is integral of nu of EX d of mu X, okay? And you do the same thing for the integral along Y, and you get this E is inside C. So E will satisfy everything in star, so E is inside C. So based on these two, we show that, first of all, the boxes are inside C, and C is closed under finite disjoint union, and F is just finite disjoint union of these boxes, so F is contained in C, okay? So this proves the first part. Now I just need to show that C is a monotone class, okay? So to show C is a monotone class, I want to show two things. So first of all, I want to show that C is closed under increasing chain, okay? So let's let En to be inside C, and their increasing chain, so E1 contained in E2 and so on. And let's let E to be their union of these En, okay? So I want to know, first of all, what is the measure of EX, okay? Well, because of E is this union, you can convince yourself why this EX is also the union of the ENX, okay? This is really simple to show. And these ENX are increasing, okay? So E1X, because E1 is contained in E2, so clearly when you restrict an X, it's still satisfy this increasing chain. Okay, so this one because nu is a measure, so it's continuous along these increasing chains. So I have this is nu of enx, the limit of these. And each of these nu of enx is going to be measurable, and we have a limit, which is again measurable. And you do the same thing for y. And I need to check the measure, the product measure of this e is the integral. So this is the integral of, so I should say, first of all, because again, you have an increasing chain, so I can write it as the limit of the measure of these en, okay? Again, by a measure is continuous along these increasing chains. And because of each of these en is inside C, so let's write n goes to infinity, I can write it as the integral nu of en of x, and then I integrate the mu, okay? And each of these new function is converging pointwisely to nu of ex, okay? So this is converging to nu of ex. Everything is finite, so we can use monotone convergence. We can interchange the limits, so this becomes the integral of the limit of these. So this is just the integral of nu of ex d mu x, okay? So I show that the product measure is the integral of these nu of ex. You do the same thing for ey again. So this e is inside C, okay? So we show that C is closed under these increasing chains. And you can also do very similar thing for decreasing chains, okay? So you do En is inside C and E1 contains E2 and so on, so along these decreasing chains. So you basically the same proof, except that the only thing you need is that recall the nu cross nu of this intersection of these EI. Well, that's equals to the limit of their nu cross nu of EI, okay? It's continuous along this decreasing chain. Well, if you know the first one has finite measure, okay? But we start by assuming that mu and nu are finite measures, so this is not a problem, okay? So this follows from that our assumption that mu and nu are finite, okay? So because they're finite, their product measure is of course still finite, okay? So because of that, everything still follows. You still have a limit of the decreasing chain, including this monotone convergence. I asked you to prove it on your assignment. So you do have a decreasing chain along these monotonely decreasing function as long as the first integral is finite, okay? So in any case, I prove that C is a monotone class. Okay, so C is a monotone class. Okay, so by the theorem we proved from last video, the monotone class theorem. Let's say theorem from last video. We now know that C, because it's a monotone class, so it contains the monotone class generated by the algebra, which is the sigma algebra of F, which is equals to A cross B. Okay, so that's essentially saying everything inside A cross B will satisfy these nice properties star. So we finish this proof. There's one last thing we need to prove because we start by assuming our measure are finite. So in general, because nu and mu are sigma finite, I can find a collection of xi and a collection of yi. I can make them increasing to the whole space such that they have finite measures. So these have finite measures. All right, so then what I can do is basically I restrict myself to the xi times yi, okay? So because on these xi times yi, they are finite, so for every E inside these A cross B, I can consider E intersect these xi cross yi. Okay, that will satisfy the star. Okay, that will satisfy star. Well, because you can treat it as you pretend your measure mu and nu are just the restriction measure on the corresponding xi and yi. And in general, because xi, yi goes to the whole space, so if you want to consider what's mu cross nu of this E, well, this is the limit of the mu cross nu of these. Let's maybe just give it a name. Let's call them EI. And because of that, well, each of these EI, you prove they satisfy the star. So this is equal to the limit of nu of these EI x, d of mu x, okay? And all of these mu of x, you can convince yourself this converges to mu of ex, okay? Because your xi is increasing, okay? So because it converges pointwisely and everything is non-negative, so you use monotone convergence and you get this is just equals to the integral of the nu of ex d mu of x. Okay, and by the way, because nu of ex is a limit of measurable functions, you know this nu of ex is also measurable, so this is well defined. Okay, so this basically proves the sigma finite case.